My name is Cecil and I'm a Casterboarder. I picked up my first board almost 3 years ago and haven't been able to put it down since. This video is a crash course in the physics of Casterboarding. The Casterboard is a recreational board with dynamics somewhere between skateboarding, surfing, and snowboarding. One thing that sets this board apart from the skateboard is the fact that you don't have to keep kicking to move forward. You can stay on the board because the forward motion is generated by moving the board in a transverse wave pattern, like a snake. This propulsion occurs when the rider alternates pushing his legs in two directions and tilting the decks. It sounds difficult to coordinate, but once you've had a little practice, you'll be surprised at how natural it really is. Let's break this down. Here we have your standard Casterboard. It has two deck plates connected by a torsion spring in the middle. On the bottom, you have the casters and the wheels. Forces involved in the propulsion of a Casterboard can be divided into two categories, internal and external. The internal forces come from the components of the Casterboard itself. These include the friction of the bearings rubbing against each other, the spring force, centrifugal force, and gyroscopic spin. The external forces are due to gravity, inertia, contact with the ground, and contact with the atmosphere. Casterboard, like a bicycle or rollerblade, is a single-track vehicle, meaning that the path of the wheels fall in line. Because the board has only one point of contact with the ground, it acts as an inverted pendulum, which means it will fall over unless balanced. If you've ever tried to balance on a bicycle while it was stationary, you understand how difficult it can be. In order to balance, we need to get the board in motion. Like a bicycle, a Casterboard has a certain degree of self-stability. This is due to the gyroscopic forces. The faster the wheels spin, the more stable the balance becomes. Think of spinning a top, or in this case, a coin. When you first spin it, it's going very fast and will balance nicely, but as it slows down, it loses stability and eventually falls over. Let's see this in action. Thanks to the angle of the caster, the rider has yet another advantage to keeping the board stable. Watch as I try the same thing with this modified board, which has no angle and rotates freely 360 degrees. As you can see, this version of the board is pretty much useless. Let's look at the advantages of the angled caster. Displacing the vertical axis changes the way the wheel comes in contact with the road. Due to the tendency of a wheel to move in a straight line while in motion, turning the angled caster creates increasing amounts of friction the farther it's turned. This increase in friction limits the range of motion, adding more stability and giving the rider the ability to turn. Due to the complex mechanics and nonlinear nature of this motion, I was unable to find any formulas that were understandable at the introductory level of college physics. Instead, I will explain the principles behind another method of propulsion common in board riding. This is known as dropping in. Standing stationary on top of the ramp, known as a quarter pipe, I represent potential energy. As I start on the ramp, I represent the potential energy becoming kinetic. At the bottom of the ramp, the curve changes the direction of my motion. The centrifugal force involved acts as though it adds weight to the rider, creating extra friction between the wheel and the concrete. A significant amount of speed could be lost. However, thanks to a technique known as pumping, much like a kid pumps his feet on a swing, the rider is able to use work to gain extra velocity. And as a final note, if you do not lean properly in this technique, the board will flip you into the air and you will rotate about your center of mass. The end.